So let's go ahead and take a look at a couple of additional examples of Coulomb's law. What we have here, we have a situation right here where we have three positive charges, each of them 1 centimeter apart, and a magnitude of 1 nanocoulomb and 2 nanocoulombs. Okay. What we want to do is we want to find out the force on this 1 nanocoulomb charge. So when we look at this diagram, we can see, because these are all positive charges, we're going to get repulsion forces. Okay, so the force on this 1 nanocoulomb charge because of this 2 nanocoulomb charge, and we'll call it Q1, we'll call this one Q2, and let's call this one Q3. So the force on Q3 because of Q1 will happen off in this direction. Okay. And the force on Q3 because of Q2 will go off in this direction. Okay. So let's go ahead and go through and draw a free body diagram of this. So here is Q3 right here, and we're going to have two forces on it, one off in this direction and one off in this direction. And we can see from our diagram that the angles here are going to be 60 degrees. Okay, so let's go ahead and start going through this and figuring out what what these forces are. Okay, we'll call this one force of 2 on 3, and this is force of 1 on 3. So we start out with Coulomb's law for each force. So let's do force 1 on 3 first. So we're going to have Q1, Q3 over r squared. So our setup looks like this, and our solution is this. So then let's go ahead and take a look at F2 on 3. We'll set up F2 on 3 like this, and it is, of course, 1.8 times 10 to the negative 4 newtons. Okay, so the next part of this is going to be finding the x and y components of each of these forces, F1, 3, and F2, 3. So remember, our diagram looks like this, and what we're going to do is look for F1, 3x here, F2, 3x here, and then each of them will have a y component up this way. So, and what we can see from this is that because F2, 3 and F1, 3 are the same size, same magnitude, we're going to end up with the same magnitude of components, x and y. The only difference is going to be is that F2, 3x here is going to be a negative. So when we go about doing this, we're really only going to need to find F1, 3x and F1, 3y, and then just remember that F2, 3x is same magnitude but a negative of F1, 3x. So F1, 3x will be F1, 3 cosine theta, and it ends up this 0.9 times 10 to the negative 4 newtons. Great, so let's go ahead and take a look at F1, 3y. And when we do that, we see that F1, 3y ends up this 1.56 times 10 to the negative 4 newtons. So great, let's take a look at what we know, right? We've got this situation here, and we have F in our x direction, we have F1, 3x is this 0.9 times 10 to the negative 4 newtons. F2, 3x is going to be a negative 0.9 times 10 to the negative 4. F1, 3y will be a 1.56 times 10 to the negative 4. and F23y will be 1.56 times 10 to the negative 4. So that when we combine these, we end up with components, our net force components end up being 0 newtons for the x direction and 3.12 times 10 to the negative 4 newtons for the y direction. So now we only have a force in the y direction, so our answer, our net force, is this 3.12 times 10 to the negative 4 newtons straight up. So let's take a look at another example. Here we have two 3-gram spheres that have been charged equally, hanging from 1 meter long threads. We don't know what the charge is. We do know that the charge was, these were charged equally, and what we want to do is figure out what that charge was. So we're going to start by drawing a free body diagram for each sphere. So for this sphere and this one. So on the left-hand sphere, we're going to have a weight here. And there will be a tension here. And we know that there is an electrostatic repulsion force here. And on the right sphere, same thing. We got a weight, we have a tension, and we're going to have an electrostatic repulsive force right there. So because these are equally charged, we really only need to focus on one of these spheres to begin with. So let's take this one that's on the left here. We're also going to know that this angle here is 20 degrees. So we're going to start out thinking about our net force on this thing. It's just hanging there. So the net force is going to be 0 newtons. Our electrostatic force is off to the right, off to the, and so this is our x direction. Our electrostatic force is off to the right. We're going to have a tension in the x direction that is negative, and that equals 0. Okay, and so when we plug in our expressions then for the electrostatic force here and the x component of the tension, this is what we end up with. And we realize that because these charges are charged equally, we can just simply square Q. But what we don't have here is we don't know this tension here. So great, let's go ahead and look in the y direction. In the y direction, our net force is also 0. We have Ty and a weight. Our y component will be equal to that weight, and therefore we have an expression for tension that we can then take and put in right over here. And so when we do that, we end up with this expression, this equation. So let's go ahead and plug in some numbers to see what this looks like. Now, to keep, just to see that if you're really listening, let's take a look at something on this here. Let's look at this right here. This is our distance, right? It's supposed to be our distance. Let's go back for a second and look at our original diagram right here. So here is, we have these 1 meter long threads, right? And we have Coulomb's law right here. This R in Coulomb's law needs to be the distance between the charges. This distance right here. So what we need to do, we need to look at what this distance is. There's our R, okay? So when we come back down to our equation here, okay, we need to realize that this R is not the 1 meter. We need to figure out what that is. Let's do that over here. So if we call the length of this thing L, the length of the thread L, and this distance of it, this is half the distance between, right? If we want to know, we can see that this makes us a nice little triangle right there. We want to know what this distance is right here, this side is here, we know this angle, we know the hypotenuse, we can use a sine function and call that side x. So that x equals L sine theta. And because this is twice that distance right here, our expression for R down here should be 2, this should be 2L sine theta. Okay? So let's rewrite this. So this is what it should be. This is what we look like. Just checking to see if you're listening. And when we plug in the numbers, here's what we get. Just like this. And then as we begin to solve, we will end up with 7.46 times 10 to the negative 7 coulombs is our charge on each sphere. Well, there's 2 more examples for you with a little explanation. Have fun.